All right, let's dive right in. If you're anywhere near the world of power distribution engineering, you know for a fact that keeping a grid stable, well, it's a massive, monumental task. Today, we're unpacking a really fascinating 25-page engineering spec document, the PPMC-DS-01 from 2026, to totally demystify how the Asset Performance Management System, or APMS for short, acts as this ultimate, unyielding protector for pole-mounted distribution transformers. We're going to break down the highly technical anatomy of this grid protector piece by piece.
Here's our roadmap for this explainer. First, the evolution of APMS specifications. Second, decoding APMS alphabet soup. Third, the brain, the SMCD. Fourth, the muscle, MCCB and contactors. Fifth, the senses, CTs and OTL. And finally, number 6, the armor, APMS enclosure.
Starting off with Section 1, Evolution of APMS Specifications. Let's map out the timeline, because these critical specs didn't just appear out of nowhere. They actually evolved over almost 2 decades of intense field testing and policy shifts. We start way back in 2007 with the foundational DDS-76 framework. Then, a massive shift happens in October 2021 when the federal cabinet stepped in and mandated a uniform grid design across the distribution sector. That push for standardizing things led straight to the crucial February 2026 LESCO field tests. Those tests were a real game changer, proving we could actually add new oil temperature and level monitoring safely. And all of that, it culminated in the comprehensive April 2026 release of the APMS standard we're breaking down today.
Moving on to Section 2, Decoding APMS Alphabet Soup.
Okay, before we crack open the machine itself, we really need to decode the, let's be honest, incredibly heavy technical jargon here. Consider this your ultimate cheat sheet. In engineering docs like this, it is so easy to get totally buried in acronyms, right? But matching them to their real-world jobs clears things right up. APMS is the whole unit, the Asset Performance Management System. The SMCD is our command center, or the brain. The CT, or current transformer, and the OTL, which is oil temperature and level, act as our senses. And the MCCB, the molded case circuit breaker, alongside the MC, the magnetic contactor, those are our muscle. Keep these tucked in your back pocket because they are the core building blocks for the rest of this explainer.
All right, Section 3, the brain, also known as the SMCD.
With our acronyms sorted out, let's examine the actual command center, the smart metering and controlling device. Think of this as the grid's neural network. Seriously, it's not just a basic meter, it is highly intelligent. It performs real-time energy audits right at the transformer level and handles remote communication back to a head-end system using both traditional SIMs and modern eSIM tech. It even has 2 programmable thresholds. One triggers an early warning alarm, and the other triggers a hard physical trip to protect the system. Oh, and since it lives outside in the elements, its printed circuit boards have a special conformal coating just to protect those delicate electronics from moisture and dust.
But here's the thought. What exactly happens to this brain when the power grid totally fails? Reliability is everything here. The spec actually mandates a specific lithium thionyl chloride battery with a minimum capacity of 2,000 milliamp hours. So even during a total catastrophic blackout, this highly durable battery guarantees the SMCD keeps its real-time clock, calendar, and multi-rate programming running continuously for at least 5 years. 5 whole years. It basically gives the system perfect memory during the absolute worst-case scenarios.
Next up, Section 4, the muscle, the MCCB and contactors.
If the SMCD is the brain doing all the heavy thinking, we need to look at the muscle that physically executes its commands. And there's a really brilliant division of labor going on here. For your daily non-fault switching, like scheduled load management, you rely on the magnetic contactor. It's an industrial-grade switch mechanically interlocked to prevent it from rapidly flipping on and off, which causes a highly damaging effect we call chattering. But here's the kicker. The magnetic contactor is explicitly not a protective device. For protection, you need the MCCB, the molded case circuit breaker. The MCCB is your ultimate failsafe against catastrophic short circuits, featuring adjustable magnetic pickup settings that kick in the moment the current spikes to 5 or 10 times the normal levels.
And in these situations, speed is literally everything. When a severe short-circuit fault hits, that MCCB muscle has to trip instantaneously. And the spec doesn't leave instantaneously up to interpretation, it strictly defines it as under 50 milliseconds. That lightning-fast reaction time is exactly what stands between a healthy transformer and catastrophic, irreversible damage.
Now you might be wondering, how does the brain know exactly how much current is flowing to command that muscle? Well, it uses current transformers, or CTs. Looking at the exact ratings straight out of the spec, you can see just how precisely calibrated these components have to be. For a small 25 kVA transformer, you'd use a 50 to 5 amp ratio. But if you scale that all the way up to a massive 630 kVA transformer, you need a heavy-duty 1000 to 5 amp ratio. Getting this calibration right is absolutely crucial for the whole system to function safely.
Let's move to Section 5, the senses. That's the CTs and the OTL. We just talked about the CTs sensing current, but the 2026 specs actually introduced a completely new physical sense to the machine: oil monitoring. The oil temperature and level sensor, or OTL, gives the grid a vital early warning system. Let's walk through this tripping logic step by step. Step 1. Detection. The internal sensor, which has to withstand 6 psi continuously, notices the mineral oil, which cools the transformer, dropping to a dangerous level. Step 2. Communication. It immediately flags this drop to the SMCD, which logs a low oil level event. Step 3. Action. Based on its programming, the SMCD fires off an alarm to the head-end system and physically commands the MCCB to disconnect the load. It essentially intervenes right before the transformer overheats and destroys itself. Pretty smart, right?
Okay, so we've got delicate eSIMs, highly precise measurement logic, and instantaneous tripping mechanics. But this brings up a massive, very practical question. How on earth do you protect all this highly sensitive computing technology from the harsh, dusty, and honestly sweltering real-world conditions it's going to live in for decades?
Which brings us to our final component, Section 6, the armor, or the APMS enclosure.
Let's transition from those delicate internal electronics to the heavy-duty exterior holding the whole shebang together. The physical housing is basically an armored vault. According to the structural specs, the body and the door have to be built from high-grade steel sheet, anywhere from 1.6 to 2.3 millimeters thick. But just being strong isn't enough. It has to be totally sealed. By using specialized neoprene rubber packing and specific powder coating over sandblasted steel, this enclosure is engineered to hit a strict IPX5 protection class. That means it is heavily resistant to both thick dust and high-pressure water jets.
And to top it all off, the spec dictates that this entire armored ecosystem must be tested and proven to survive a blistering maximum ambient temperature of 55 degrees Celsius. Think about that for a second. You've got a sealed steel box baking in 55-degree heat while it's still accurately processing data, running cellular communications, and physically switching hundreds of amps of power, all without a single failure. It is seriously impressive engineering.
It's just incredible to see how these engineering standards evolve. What started out as basic guidelines has morphed into a rigorous blueprint for a highly intelligent, self-preserving grid protector. As these asset performance management systems roll out, they're doing way more than just measuring current. They're extending the life of our infrastructure and actively preventing catastrophic blackouts. Which leaves us with a fascinating thought to wrap up on. As these APMS units continue to gather incredibly precise field data, what will the even smarter distribution transformers of 2030 be able to teach us about power management? Thank you so much for joining me on this explainer.